Welcome everyone. For today's prep, we're going to be looking at continuously compounded interest, and we're going to start with the formula and see an example. So the formula here that we're going to be using is A of t is equal to P times E raised to the RT. So there's a lot of little different pieces here to this formula. So first of all, P here is the principal amount. So this is how much money we initially deposit into our account. So if we remember the scenario, we're putting money into a savings account and then we're not touching it. So this is our initial investment. The interest rate is R, and this is the interest rate that the bank pays us per year. And normally the interest rate is given as a percentage, and when we use this formula, we have to use the decimal. So just a little note there. We want to make our interest rate a decimal. T represents the number of years that we're going to let our investment sit and accumulate interest. And then A of t is the output of our function. So this is telling us our account value after t years. So when you think of principal, this is kind of like our starting value or our present value. And you can think of the output of our function as what happens in the future. All right. So let's go to an example. We're going to talk more about this formula in class and how it relates to kind of discrete compound interest. But I want to look at an example where we just get a little practice working with this and seeing the types of questions that can be asked. So we're going to go down to this one. So we're going to suppose that $1,000 is invested at 6% interest compounded continuously. So we're going to give the formula for A of t. So we see this phrase compounded continuously. So that immediately tells us what formula to use. So we're using this A of t is equal to P e to the RT. Now, what other information do we have? Well, we're starting with an investment of $1,000. So this is our principal. And our interest rate is 6%. So our R value in this case, we're not going to use the 6%. We're going to use 0.06. So we're going to use that as a decimal. All right. So again, we're told our principal, we're told our starting investment. We have our starting interest rate, or our interest rate, doesn't change. And we also know we're dealing with a continuously compounded interest model. So we're using essentially this exponential growth function. All right, so let's plug the pieces in. So A of t, we know our principal is 1,000, so we'll plug the 1,000 in there. And then we know what R is, so we'll plug that in. So we end up with 1,000 times E raised to the 0.06 times t. And the output of this function has the same units as our principal. So our principal is in dollars, so our output here will also be in dollars. All right, so this function now, we can use this to help us make predictions about how much money will be in our account after different lengths of time. So in part 2, we want to know how much money is going to be in the account after 6 years. Well, all this is saying is we're just going to plug t equals 6 into our account balance formula. So we're going to evaluate a of t when t is equal to 6. All right, well, let's do it. So we're going to plug 6 into our account balance formula, and we're plugging 6 in for t. So when we do that, we get 1,000 e to the 0.06 times 6. And for these problems, perfectly fine if we just leave it like that. All right. Let's look at the next one. So after 6 years, at what rate is a of t going to be growing? So when we see that word, rate of change is a derivative. So this one is asking us to evaluate a prime of t when t is equal to 6. So we want to know how much our account balance is growing after 6 years. So we want to know what the value of our derivative is after 6 years. That'll tell us the rate of change. So first of all, we have to calculate our derivative. So we got to calculate it. All right, so we want to get a prime, and we're going to differentiate our account balance formula. So let's actually use our formula we found back in the first part. So 1,000 e to the 0.06 times t. We're going to differentiate this whole thing. And the 1,000 is a constant multiple, so nothing really happens with that. That's just going to stick around. And we can focus in on differentiating this exponential part, but there's a little bit more going on in the exponent there than just t. So we have to use our chain rule to get this derivative. So when we do calculate the derivative, the 1,000 is in front, the exponential portion stays exactly the same, and then we multiply by the derivative of that stuff in the exponent. So in our case, the derivative of that stuff is 0.06. So we're multiplying by 0.06. So again, the 1,000 constant multiple stays the same. Derivative of the exponential also stays the same. But then we multiply that result by the derivative of our exponent term. And if we clean that up, 0.06 times 1,000 is just 60. So we get 60 e to the 0.06t. All right, so now we're ready to evaluate. So we do that second. So we'll plug in our t equals 6. And when we do that, we get 60 e to the 0.06 times 6. And what are the units going to be here? Well, it's a derivative, so it's going to be the units of our original function divided by the units of time. So this is going to be dollars per year. And just to help conceptualize this a little bit, what would this be? What if we did calculate this as a decimal, what would it be? So this would be approximately $86. And it would be per year. So what this is telling us is once we reach that 6-year mark, well, so we put the $1,000 in, we let it sit, our account's accumulating interest during those 6 years, and once we reach that 6-year mark, if we were to let it sit for an additional year, we would end up with approximately 86 extra dollars in our account by the end of year 7. So this is kind of giving us an idea of what to expect over the course of the next year. So over the as year 7 progresses, we'll see approximately $86 more. All right, so let's try one more of these. How much time will it take for our initial investment to double? So we're putting in 1,000, and we want to know how long is it going to take until we have double that. All right. So what is this question actually asking? It wants us to figure out when does A of t equal double our initial investment. So we know what our initial investment is. It's 2,000. It was 1,000, so double that would be 2,000. But turns out we can just leave that as 2 times our starting principal. All right. So what we're going to do is we're going to take our function and we'll set it equal to double our starting value. So our account balance formula is this 1,000 e to the 0.06 times t, and we're going to set that equal to 2,000. So double our initial investment. Now when we do that, this is an exponential equation. And we've seen a strategy for how to solve these. So our strategy is to first solve for the exponential piece. And then once we've isolated that exponential piece, then we apply the natural log function to both sides so that we can get the t out of the exponent. So first of all, let's divide both sides of this equation by 1,000 so we can isolate the exponential term. So we end up with e raised to the 0.06t equal to 2. And again, when you do this, just leave some spaces so you have some room to put in the natural log function. Once we've isolated the exponential part, now we're going to apply the natural log function to both sides. That's why we need those spaces. And the reason why we use the natural log function is because this is the one function that cancels off the natural exponential function. So we're able to cancel it off. And when we do that, we end up with the equation 0.06t is equal to natural log 2. And even though it's a decimal and natural log 2 is kind of fancy looking, these are just numbers. So we want to get t all by itself, so we're going to divide both sides by that decimal. And we end up with t is equal to natural log 2 divided by 0.06. And our units for t is years. And just to help, again, conceptualize here, what would this be? If we write out this as a decimal, what would this be? Well, this would be approximately 11.55. So roughly 11.5 years it would take for our account balance to double. And that's all thanks to the interest that's accumulating in our account during that time. All right, so we'll practice some more examples of compound interest in class, and we'll just see some different games that we can play with looking for maybe interest rates or time to double or time to reach a certain future value. So there's all sorts of different games we can play with this this formula. So we'll see you then. Bye-bye.